Zagier has this paper with the following titles from 1981, and in it there's this theorem that is what I'm going to refer to when I say automorphic regularization. And I should caution that this term, automorphic regularization, is not very common in the literature. I've seen it once or twice, but generally speaking, if you say this, people are not going to know what you mean, so you're going to have to clarify. But I'm going to explain this, and in this lecture, I'm going to explain it for level 1 and trivial character. You can generalize this, and you can generalize it quite a bit, but this paper and this lecture are going to be about just level 1. So let's start with some setup that we'll need to state the theorem. So f is going to be this automorphic function that has the following Fourier expansion. So I'm going to say that's a sum n from minus infinity to infinity, so including 0, of a sub n of y e n x, so just a Fourier expansion, and I'm going to say that this is an automorphic function of level 1 and weight 0, i.e. it's SL2Z invariant. And we're going to have to talk about the structure of this constant term a little bit. We're going to have to break it down. So suppose that this constant term a0 of y, and I'm going to break it into, say, 3 pieces. So I'm going to call it phi plus of y, and then I'll say a phi minus of y, and I'll define all of these in a second, and then I'll say a whatever d of y, and the assumptions I'm going to have are that such that, so first I'll start with d of y. D of y has to be of exponential decay, so this is going to be less than y to the n for all real numbers n as y goes to infinity. So it just decays faster than any polynomial. And then I will say that y plus of y is equal to the sum, or over some indices of these, let me just write it this way, some coefficient ci, and then it's going to be some power of y, alpha I, and then some power of log of y to some other power. And the plus is going to, here, is going to refer to, I'm going to also require that these alpha i's are all at least 1/2 in real part. So it's going to be that piece, and then this phi minus of y is going to be the same thing with different different ci's and y to the alpha I tilde log y to the beta I tilde, and here it's going to be with the real part of alpha I tilde is strictly less than 1/2 for all I. So breaking this constant term into three pieces, and the reason to do this is so that we can we can state this theorem that's going to be, automorphic regularization. So if you so here's what the theorem is going to be. If you look at so the assumption is if phi plus of y equals 0, meaning you don't have any terms that look like this, right? Your entire constant term of your Fourier expansion is just some powers of y that all have real part of the power strictly less than 1/2, and then some piece with exponential decay. Then this inner product of f with, and I'll just say this Eisenstein series, z s bar, this is the level 1 weight 0 Eisenstein series, is in fact going to be equal to this inverse, just this normal Mellin transform of just the part that decays exponentially. So this is dy, and then here I'll have a y to the s minus 1 dy over y. Right, so you only need to care about this part of rapid decay. You can completely forget about this phi minus. So normally, if you were to do this, just putting your head down and just calculating, what you normally get is phi minus y plus dy times y to the s minus 1 dy over y. So in other words, you can completely ignore the phi, the minus term, when you're doing unfolding. And this is pretty cool, and it's not at all obvious, but it's true. So let me give an example. So last time we talked about this product of this completed Riemann zeta function. So recall I'm defining this thing to be pi to minus w gamma of w zeta of 2w with this level 1 weight 0 Eisenstein series, and then for a positive in integer k, I'm multiplying by the holomorphic weight k Eisenstein series. So this is the holomorphic E. And this thing we can just write down its Fourier expansion, because we know the Fourier expansion of this first factor, and we know the Fourier expansion of the second factor. So this is equal to completed Riemann zeta function times y to the w plus completed Riemann zeta function at 2 minus 2w y to the 1 minus w. That's the constant term. And then we have a sum n not equal 0, 2 times the absolute value of n to the 1/2 minus w sigma 2w minus 1 of n. Here I'm using the convention that that sigma of n is the absolute sigma of the absolute value of n. And then we have the usual Whittaker function. So this is going to be just the Fourier expansion of this weight 0 Eisenstein series. And then we also know the Fourier expansion of this holomorphic Eisenstein series. It's 1 minus 2k divided by the kth Bernoulli number, and then sum n from 1 to infinity, sigma k minus 1 of n. We don't need a complex conjugate here because this quantity is real. Then I'm going to write it as e to the minus 2 pi ny e of minus nx. And here the minus sign here comes from the complex conjugate. Normally this would be an e of nx, but the e to the 2 pi I nx becomes e to the minus 2 pi I nx when we take the complex conjugate, this complex conjugate right here. So we have this, and what is, we're going to have to take this constant term, and we're going to have to break it up into these three pieces. So what is the constant term? So the constant term is equal to, well, there are two ways we can get a constant term. We can either take the constant term from this factor and the constant term from this factor, or we can take an n from this factor and an n from this factor. So let's write out both of these separately. So the first one that we get from taking the two constant terms is there's lambda of 2w, y to the w plus k over 2 from here, and plus lambda 2 minus 2w, y to the 1 minus w plus k over 2. And then the piece that we get from matching the n's, well, it's going to be a sum n from 1 to infinity. Every time we have a term here, we can find an associated term here. And then we have our coefficient is 4k over the kth Bernoulli number, right, the 2k times the 2. Our n is positive, so we can drop the absolute value, and the 1/2 minus w sigma 2w minus 1 of n sigma k minus 1 of n, coming from these two things. And now let's start writing out the y dependence. So here we have a k to the w minus k of w minus 1/2 2 pi ny. And then we have this exponential right here, e to the minus 2 pi ny. And then what power of y do we get? Well, we have a y to the k over 2 here, and we have a y to the 1/2 here. So we have a y to the k plus 1 over 2 as the y dependence. So this is the constant term of this function. And when we think about this theorem morally, what we're saying is that as long as we can get rid of all the terms in the part that has a power, then we can take this inner product where we just ignore, where we get rid of the terms that have a power where the real part is at least 1/2. We can possibly leave some where the power is less than 1/2. Then when we take this inner product, we can just ignore the remaining powers. And that was the problem when we were trying to take the spectral decomposition of this thing, where we took this inner product with this Eisenstein series, and it wouldn't converge. So here, of course, you may have, you probably are going to have these powers be greater than 1/2 in real part, because k is going to be big, and w, well, regardless of what it is, at least one of these two things is going to have real part greater than 1/2. So the idea is going to be to define what I call a regularizing function. So I'm going to define R of z to be, and I'm just going to choose some linear combination of Eisenstein series. So I'm going to choose this lambda 2w e z w plus k over 2. And then I'm also going to take another term, lambda 2 minus 2w e of z 1 minus w plus k over 2. And I call this a regularizing function. Again, this is non-standard. If you say this, people are going to have no idea what you mean, but okay, I'm going to call it this. And now let's look at the difference. V of z, so for v, I'm going to call this function v. So let's look at this difference, v of z minus r of z, and this has some constant term, right? So what's the constant term? The constant term is going to be lambda, well, let me just copy paste, huh? So the constant term is just the constant term of v, and then let's look at what happens for the constant terms here. Well, here, what we're losing from this r of z, we have this, we're getting a minus, and here it's going to be just lambda 2w y to the w plus k over 2. That's coming from the y to the w plus k over 2 from this thing multiplied by this lambda of 2w. And then we have a lambda of 2 minus, so it's going to be lambda of 2 times the argument here. So 2 minus 2w minus k over lambda of 2w plus k times the lambda of 2w from in front here, and then a y to the 1 minus w minus k over 2, right? So it's 1 minus the argument, so that's this. So that's the first term here. And then what about the second term? Well, here we're going to have a lambda of 2 minus 2w y to the 1 minus w plus k over 2, right? Again, it's just y to the power and then multiplied by this thing in front. And then finally we have this lambda of 2 minus 2 times the argument. So here it's 2w minus k divided by lambda of 2 minus 2w plus k. So this is going to be lambda of 2 times the argument. And then we have a lambda of 2 minus 2w from right here. And then a y to the 1 minus the argument, so w minus k over 2. So that's what the constant term is. And of course we see that there is this simplification. What a coincidence. So of course you can do this, you can choose the regularizing function so that this happens, right? And that's exactly what was done here. You can see what you're going to need to cancel. You're going to need to cancel out these two terms. So just pick a linear combination of Eisenstein series that does that. So let me just rewrite for emphasis. It is, it's minus lambda 2w lambda 2 minus 2w minus k over lambda 2w plus k y to the 1 minus w minus k over 2, and then minus the second thing here. So lambda of 2 minus 2w, lambda of 2w minus k, for lambda of 2 minus 2w plus k, y to the w minus k over 2, and then we still have this part of the constant term right here. Okay, so this is the constant term of this difference, v minus r. And let's make some assumption. Let's also assume and this is mostly for simplicity so that we don't have to worry about other cases. So let me assume that the real part of w minus 1/2 is strictly less than k over 2. And what that implies is that 1 minus w, or the real part of 1 minus w minus k over 2 is strictly less than 1/2, and the real part of w minus k over 2 is strictly less than 1/2. And what that means is that this constant term, well, this part is going to be phi minus in the notation above, right? So we, right, for this theorem, we broke the constant term into 3 pieces: the powers of y that had real part at least 1/2, the powers of y that had real part strictly less than 1/2, and then this part of rapid decay. So this is the part, these are powers of y, and we know by assumption here that they have real part less than 1/2, and this part here, this is going to be our d. This is our part of rapid decay, because this k-Bessel function and this exponential function, I mean, they decay exponentially in y as y goes to infinity. Doesn't matter what this power of y is. You're always going to be less than any polynomial power of y. So we have this, and then what does this imply? Well, this implies that this inner product of v minus r, right? So this difference of the v was this function that we were interested in, and r was this regularizing function chosen as some linear combination of Eisenstein series chosen so that we cancel out the big powers of y in the constant term. And when we take this inner product with our Eisenstein series z s bar, then this theorem from Zagier, right? The theorem said that this inner product was equal to the Mellin transform of just the part of rapid decay. You don't have to care about these powers of y. If you went and you just unfolded naively, these powers of y would appear in your unfolding process. You will write them down from one line to the next, and the magic of this theorem is that you can just completely ignore those terms. You can just pretend that they're not there. They're somehow guaranteed to cancel. So this is equal to this Mellin transform of, okay, this thing, which probably was already on my clipboard. So it's this integral, but we have a y to the s minus 1, right, which is what you get from unfolding. The theorem does explicitly say that you get y to the s minus 1 here, but it's really, it's the dy over y squared in the usual measure, the Poincaré measure. So I'm going to take that minus 1, and I'm going to stick it here, just to have something that's more familiar. Hello? Hello? Oh no, what have I done? Okay, well. Oh no, oh no, what have I done? Terrifying. Let's try again. Okay. So this will be y to the s plus k minus 1 over 2 dy over y. And then here, we can rearrange this a little bit. Sum n from 1 to infinity, 4k over the kth Bernoulli number, n to the 1/2 minus w. None of this depends on y. And then for the integral that we get, well, we can use that formula of Gradstein and Rizek. So, okay, we'll get this integral k w minus 1/2 2 pi ny e to the minus 2 pi ny y to the s plus k minus 1 over 2 dy over y. And this is, I believe it is what, Gradstein and Rizek 621.3. But it gives you a formula for this, and normally there's a hypergeometric function that appears, but we're quite lucky where this argument of the k-Bessel function is equal to this thing in the exponential, and that causes the z in the hypergeometric function to be 0, and so the value of the hypergeometric function is 1. So we end up getting some n from 1 to infinity, same thing in front for k over the kth Bernoulli number, n to the 1/2 minus w, sigma 2w minus 1 of n, sigma k minus 1 of n, and then I believe, and I'm not going to look it up right now, but I believe what you end up getting here is, I want to say this is 4 pi n to the s plus k minus 1 over 2, and then should have some gamma functions. So the gamma function should be s plus k minus 1 over 2 plus w minus 1/2 gamma of s plus k minus 1 over 2 minus w plus 1/2 divided by gamma of s plus k minus 1 over 2 plus 1/2. Again, this is from memory, so forgive me if I get this wrong. And I guess we can clean this up a little bit more, right? We're going to get minus 4k square root pi divided by the kth Bernoulli number times 4 pi to the s plus k minus 1 over 2. And then we're going to have our gamma functions, gamma s plus k minus 1 over 2 plus w minus 1/2, gamma s plus k minus 1 over 2 minus w plus 1/2 divided by gamma of s plus k minus 1 over 2 plus 1/2. And then we have this Dirichlet series, sum n from 1 to infinity, and it's going to be sigma 2w minus 1 n sigma k minus 1 n divided by n to the s plus k minus 1 over 2 plus w minus 1 half, if I haven't messed anything up. So this is an example of how you can use this theorem of from this paper that I call automorphic regularization, where when you have this level 1 automorphic form and you want to take an inner product with an Eisenstein series, if normally you just get the Mellin transform of the constant term. But that's bad news if your constant term has powers of y in it, because the Mellin transform of some power of y is never going to converge. And the theorem from this paper, the theorem of automorphic regularization, says that as long as all the powers of y are strictly less than 1/2, right? So as long as there are no powers that have real part of y at least 1/2, then you can evaluate the inner product by just considering the part of rapid decay. So I guess it'd be prudent here to go into show you what the theorem from the paper says, so you can read it if you're wondering anything and you want some details. So the full theorem is as follows. So you see here what it's saying is that, well, at least the statement is true in this bound. So I guess I will amend that here. So if this real part of S, it has to be in this interval between max of alpha I tilde, or the real part of alpha I tilde. Hello? The max of the real parts of alpha I tilde, where alpha I tilde is this power of y, and 1 minus the max of the real part of alpha I tilde. So it's not going to hold for any s, but it will hold for s in particular on the line 1/2, right? If the real part of s is 1/2, then this holds. And when we're doing spectral decomposition, that's what we're going to get. So this is the full theorem, and the part that this lecture was really about was this last part, right? That if you look at this Mellin transform of the part of the constant term without the powers of y, then in fact the inner product is equal to that Mellin transform, which is, again, not at all obvious. And then the paper goes on to give some examples. In particular, it gives an example, it's a triple product of Eisenstein series, which is also going to be a case that is interesting to us.